Hello, everyone. My name is Lingyang Sheng. I'm working in Peking University in China. It's my pleasure to give a talk for the 30th anniversary of HOB Comsoft Thailand chapter celebration. And the title is Reconfigurable Holographic Surface for 6G. So this is outline of our presentation. I will first talk very briefly about the 6G communications. So as our known, the world communication system is actually evolved every 10 years. We're starting like the first G, and we are now in the fifth G, and in the next perhaps 4 or 5 years, and 6G will come. So in the wireless communications, and typically based on the applications, particular specific scenarios, such as like the 4G is going to support or has already successfully support mobile internet, and 5G, and we are talking Internet of Things, and in 6G, and people are recently talking about a lot about holograph communications, and holograph is a very interesting research topic, which can support very high data rate and also deliver the smooth, like high capacity the videos, for example. So this slide and shows the terms of and the interpretations of holographic MIMO communications or holographic communications. So we try to explain this in three aspects. And from the theoretical ones, for example, and it gives like or defines continuous aperture packing infinite number of antennas. And enabling techniques is another aspect. It can support the ultra high spatial resolution by extremely large scale antenna arrays. And finally, which is most important, and all the communications is facing or solve the real problems. So it will support like a fully immersive and real-time 3D and video experiences. So, but anyway, the enabling techniques is quite important in order to realize holographic communications, and the one possible way is holographic MIMO techniques. So this slide shows the what is MIMO, and MIMO is multiple input and multiple output systems, and based on Carl-Shannon theory, the data transmission rate or capacity is proportional to the number of transmit antenna or receive antennas. And in the fourth generation, the MIMO technique, multiple antennas, has already been used to support high transmission rate and also protect the transmission errors. And in 5G, and the current system is using massive MIMO, like the 46 transmit antennas. In the next generation, so and the antenna number will increase to the thousands for high data rate, and this is kind of ultra large scale multiple antenna technique. So to design or implement the ultra massive MIMO, there are a number of methods. The traditional methods are too commonly used is phased array, which is for 5G. But the problem, it has very costly hardware component and consumes particular high power. Another commonly used method is reflecting arrays, which has been widely used for satellite. And the major problem or bottleneck is it hard to integrate, and the flexibility is quite limited. So to consider or to realize ultramassive MIMO, and we can see the current barriers are so much. So because of the limited scale and high energy consumption and unacceptable costs. So we need to find a new technology or new method to serve as an alternative instead of the antenna array. Holograph antenna, actually, which was first invented in the last 1950s, and it has a number of the benefits or advantages over phased array or the reflecting antenna in terms of large scale, because it use or consists of designed by numerous metallic patches. It has very low cost and low power consumption. And since it was first invented in last 40, 60 years ago, and it was widely applied in military applications and also the emergent communications. So this slide and talks about very briefly the holograph antenna working principle. Actually, from the hardware constructor, the holograph antenna, this is the type of decay wave antenna. And the surface actually is composed of numerous, many metallic patches. And the feeds can be integrated in the edge of the center and in the surface. So it makes the antenna ultra thin. And the EM wave actually is output from the feed can propagate along the surface and emitted to the free space. And in this way, it's easy to be integrated in contrast and unlike of the reflecting antenna use the satellite systems. So in holographic antenna, regarding its wireless transmission, it has two major concepts of the definitions. One is holographic pattern. This is a specific geometric configuration of metallic patches. And based on the holographic pattern, when the EM waves propagating along the holographic pattern, and a specific EM radiation can be generated and to give the directional beams. So the major definition actually has the reference wave, which is the input of the feed, and the vector wave, which is the directional beam that we aim to generate. And another one is holographic pattern, is the interferences between the reference and vector waves. To generate the EM wave directional beams, and it takes or use two steps. In step one is holographic pattern recording. By replacing the metallic patches on the surface in a specific manner, and the adjacent patches can interfere with each other, and all of these can form the holographic pattern. And in step two, when the reference wave is fed on the surface, it interferes with the holographic pattern, such as to generate the directional beams. This is called holographic beamforming. Actually, so in traditional holographic antenna, it has a number of benefits, such like the it can be designed very large, large scale, and it's ultra thin and low cost and consume very little power. But actually, it has a number of major limitations. The reason is when the placement of metallic patches is fixed, the hologram antenna has or only produce the fixed beam pattern, such as it's not able to support mobile scenarios. So if we can solve this problem, and maybe we can find another way to realize the ultramassive MIMO if we solve this kind of fixed pattern problem. And that is we are going to the topic we are going to present in this slide, actually in this talk, is called reconfigurable holographic surface. And we try to apply this kind of meta surface to holographic pattern design such that the pattern can be reconfigurable. So inspired actually by meta surface, the metamaterial techniques, that is quite hot topic. The meta surface or metamaterials is sort of artificial structure that are not exist in nature. And this sort of structure can be conform or can generate a thin surface composing of sub-wavelength elements. And furthermore, we could use active components to connect these artificial structure by pin diagonals, for example, and it can realize dynamic control for pointing out beams by biased the voltage on pin diagonals to make the meta surface reconfigurable. So it has many benefits. So it can generate, as I mentioned earlier, to solve the holographic antenna problem, the dynamic beams capable of controlling EM response of antenna element. It has extremely cost and energy consumption because of the Chi pin diagonals and PCB techniques. This slide and the rest, a few discuss the RHS, like the meta surface, the working principle. In this meta surface, this is a 2D planary like structure with ultra-large number of sub-wavelength elements. And regarding reconfiguration, by controlling each element, the EM amplitude response can be adjusted. So the working principle or the working procedure can be explained in the following 3 steps. In step 1, the feeder or Shen input inference wave to the surface. And in step 2, when the reference wave arrives at RHS element, it interplays with the holographic pattern and radiate energy into the free space. And in the final step, the reference wave turns into the radiated signal in the free space, and by superposition on the free spaces, and to finally form directional beams. So this is theoretical development from the holographic antenna to the holographic intelligent surface. So the idea was first proposed by Gamma, that is quite earlier. This is the first proposal of holographic technology. And later on, the holographic technology was proposed in microwave band. And gradually, in the 2000 and a few years later, and or 3 years before, in Peking University, we first proposed this sort of RHS techniques. And this slide compares of the RHS and the recent RIS techniques. So in terms of physical structure, operating mechanism, and also the typical applications. So in physical structure, in RHS, is RF font and is integrated in the meta surface. And the operating mechanism is serial feeding, such that the typical applications and make the RHS can be implemented together with the base station. But for RIS, its RF front end is outside of the surface, and the major application is to use as the passive relays. So for RHS, and the applications can be in wireless communications to improve the spectrum efficiency and also to improve the energy efficiency. Such that actually, if we use RTX in wireless communications, as I mentioned earlier, and in contrast or unlike the phased array, in phased array, it's like a parallel transmission. But in the RTX, the signal of the reference wave is travel along the surface. It's like a zero transmission. And in the phased array, and the beam direction is controlled by the phase, but in the RHS, its direction is controlled by the amplitude. So we need to revisit the transmission and the multiple access techniques. And in the first case study, I would like to first briefly introduce this sort of multi-beam transmission by amplitude-controlled holographic beamforming. So this is the system model. This is traditional like wireless communication system. If you consider downlink, RHS-aided MIMO system with one RHS base station and K users, and this block diagram gives you the RHS-aided hybrid beamforming framework. In contrast to the hybrid beamforming for the phased array, so we only need to consider and how to perform this sort of holographic beamforming. And in the equation in the bottom of the slides, you see, okay, one term M represents the holographic beamformer, and V is the traditional beamformer. So the problem formulation is we quite familiar with. The objective is to max the triple rate. And this is a very complicated problem which can be composed into two sub optimization problems by digital beamforming and holographic beamforming. So regarding the holographic beamformer M, we can see it has two major parts, but it is represented in the element wise. And the first term is the holograph pattern, and the second term is the reference waves. And the objective is to find the right amplitude of all the amplitude and to optimize by the holographic beamforming in the this kind of optimal problems. So from the simulation result, okay, so we can see that, and the RHS-enabled system clearly can deliver very good performance. So in this case study, we show how the RHS can support multiple users. Actually, the idea is very simple. So you just mapped the transmitted data onto a single holographic pattern, and by the superposition of the multi-users and the parallel signal beams of these users are conveyed. Based on the superposed holographic pattern, the RHS controls each element to generate multiple digital beams. So this slide gives you a two-user example, and each user corresponds to a particular holographic pattern. And by submitting all the holographic pattern with the proper width, and the multi-user can be supported by this sort of HDMA technique. And in the simulation results, and we can see the two bits actually, the pin diagonals are efficient to approximate the sum rate with continuous amplitude values in the multi-user case. And one bit is enough in the single user case. This is quite an important example. So in the next few slides, and I would like to show the implementation of the system. And the target is to implement a millimeter wave RHS-enabled communication system as an alternative to phased array. So the following is the key design parameters, and we designed the system. Actually, it's based on 3GPP parameters. And in terms of the frequency, bandwidth, polarization, and also set control rate and switching speed. So this slide give you, we need to first design the element, and then to design the antenna array. And furthermore, we design the control circuit and then integration. And finally, we finish this sort of RHS, this kind of surface design. So what we can see, okay, we can, by using this RHS, and it delivers very high throughput. And I would like to also show you a video of this.
To verify the feasibility of RHS-enabled holographic radio, we implement a prototype of RHS operating at 26.2 GHz. The RHS consists of a two-dimensional array of 256 electrically controllable RHS elements. The reference wave generated from each feed propagates to each RHS element and radiates energy to free space. An RHS element capable of controlling the radiation amplitude of the reference wave relies on a complemented CELC resonator loaded with PIN diodes. Specifically, the mutual inductance of the CELC resonator as well as the radiation power of the reference wave is determined by the states of the PIN diodes. When the two PIN diodes are in the off states, the radiated power will be large. In contrast, when the PIN diodes are in on states, the radiated power will be small. The states of the PIN diodes can be controlled based on the control circuit. To verify the effectiveness of the proposed holographic beam forming scheme, we evaluate the beam pattern of the implemented RHS. The RHS can achieve the scanning angles from -60° to +60° horizontally and from -15° to +15° vertically. Based on the prototype of the RHS, we develop an RHS-aided downlink communication platform, which are composed of a host computer, 2 mm wave user equipments, UE, and the implemented RHS. The RHS consists of multiple subarrays, which is used to transmit signals. The implemented RHS prototype can support cross-polarization. The mmWave UEs serve as the mobile terminals to receive signals generated from the RHS. In the deployed RHS-aided communication platform, we transmit dual-stream signals using 64 QAM modulator. The EVM performance of the 64 QAM signal is 6.87% within 8%. In a two-user system, the data rate of the RHS-aided communication platform can reach 4 gigabits per second.
For the RHS, it has a number of field applications in applications, such as to design the satellite user terminal, UV terminal, the vehicle terminals, and also the 6G base stations. And in addition to wireless communications, it can be used for the touch sensing, like the radar systems, to improve the high spatial resolution. Because of the actually the time, I cannot give details. But anyway, so if you are interested, actually, you can go for our tutorials and in the ICCC this year and maybe a GlobalCon this year. So this is actually the outline of the tutorial. It gives the very details and all aspect of the RHS communications and also the sensing. Okay, thank you very much for this.